Good morning. My name is Jim Haldeman. I am Business Development Manager for the Lesman Instrument Company. Thank you for taking some time this morning to learn about ultrasonic flow technology. Our guest speaker this morning is Gerard Bottino from Panametrics. Gerard is an engineer who has experience in the water, wastewater, chemical, pharma, food and beverage, power generation, oil and gas, and petrochemical industries. Gerard has over 16 years invested in working with flow meters and has 12 years specifically working with Panametrics products. Gerard is considered an expert in ultrasonic flow measurement and has traveled the world sharing his knowledge. At the end of the presentation, we will open up the mics for your questions or use the question tab on the screen to ask your questions, and I will respond or I will let Gerard know of the question. So with that, Gerard, please proceed with your presentation.
Thank Jim for the introduction. You may notice that I do not have an American accent. That's normal because I'm French. So with that, we want to thank you for giving us the opportunity to present our experience around the solutions that we've deployed in different industrial segments. And I would like to start with to talk a little bit about the fundamentals of ultrasonics. Essentially, I will only focus on the transit time technology that we use and do not talk about the Doppler technique because it's not the one that is the most popular in the industrial segments we are playing. So to start with, ultrasonics, the transit time principle is somewhat very simple. We have two transducers sitting apart of the pipe, and there's a distance between those transducers that is represented here by the P, which is the path length, and there's also a projected actual length, that is the L. And you can see also there's a theta angle, and this theta angle is helping us to get a time difference between the upstream and the downstream measurement. Because when I need to go from the upstream transducer to the downstream transducer, if I go with the flow, like the green arrow you have there, it will be accelerated, while in the reverse direction, it will be decelerated. And this time difference is directly proportional to the velocity of the fluid. And it doesn't matter what fluid it is. It can be steam, can be air, can be water, can be anything, okay? And this is directly proportional, so there's nothing very complex about it. Now, if we look at what is important to know and what is measured, if we look at the velocity, which has to do with the distance between the probes, as well as the angle of the installation, all the rest is a matter of time. So in other words, when you have an ultrasonic meter, what you have is a very accurate clock. So the resolution of the time measurement is in nanoseconds. Okay, so it's extremely precise in terms of time measurement. And everything else being equal, it's only to do with the geometry of the line. So what you can notice as well is that the system does not generate any pressure drop. So in today's world where energy is looked at a resource that we need to preserve, it's good to not waste energy for nothing. So there's no pipe restriction. Therefore, there's no prone to drift or having any kind of maintenance issues, being a kind of full bore system. This technology, if you look at the way the velocity is calculated, it's not prone to drift because it's just a matter of geometry and time. So once you have the velocity, you multiply the velocity by the cross section of the pipe and you get your volumetric flow. So it's very straightforward as a technology. Because we have this kind of full bore design, there's no need to install filters or strainers, and there's no need for maintenance coming from it, right? It can measure in both directions. Obviously, if you look at the top schematic, I could have a reverse flow. The only difference I will have is that the yellow arrow will go quicker than the green arrow, and I will have a negative sign when it comes to the volumetric flow. So it can work both ways. There's no moving part inside that will be prone to wear and tear. So it's something that will last for long. And it is not influenced by the pressure and the temperature. So it's not very complex as a system. And I put that one because on the equation of the velocity, you have P and T, but that's the path length and the time. It's not the pressure and the temperature. So with this, Panametrics has been in the business for some time, with the first patent being filed in 1971. So it's a while ago. I was in my elementary school at that time, so it has been a while. So what we use also is the velocity of sound, because whether you use it or not, the system does calculate the velocity of sound of the fluid. This is not the velocity of the fluid in the line. This is the velocity at which the sound travels into a given medium. So it changes with the density, as you can see, and it changes with the temperature. So this velocity of sound is very different when you deal with gas or with a liquid. And if you can look at the kind of specific curve for water, and temperature is expressed in degrees Celsius in this case, it has a kind of strange behavior because it has an inflection point at 74 degrees Celsius, where it starts to behave like a liquid, while up to 74, it behaves like a gas. But it is very, very easy to track the velocity of sound of any medium you use. The other thing that you need to think of is what kind of frequency of transducers you need to use for you to be able to measure in an optimal set of conditions. Oops. Can you see my screen okay?
Yes, it's back. It's actually back to the
okay.
beginning slide. There you go. Now you're back.
Yeah, okay, thanks very much. Sorry for that. So in an ideal world, we would like to have the highest possible frequency, because high frequency means that you sample a lot. By sampling a lot, you have a very good accuracy. But because the sound doesn't propagate very well on long distances or with difficult environments, we need to do a trade-off. So high frequency helps with accuracy, but sound propagation is impacted by frequency. So if you think about that, if you hear someone playing music, if you are far away from where they play, you will likely hear the drums and not really the guitar. It's because the frequency is lower there, and it propagates better than the higher frequencies. So we need to find some sort of a compromise, getting a good enough accuracy combined with a very good signal capability in terms of sound propagation. So that's why that within the spectrum of the applications, for liquid applications, for very small pipes, we will use up to 4 megahertz. Like if you have a half an inch, 3/4 of an inch, 1 or 2 inch, typically that will be this kind of 2 to 4 megahertz frequency. Then as much when the pipe becomes bigger, then you decrease this frequency with liquid. So for very, very large pipes, then you will go down to the 0.5 megahertz or 500 kilohertz. If it's gas, you start only at 1 meg and then you will decrease the frequency when the pipe goes up, as well as the pressure goes down, because the sound will not transmit as well on low density than in high density. So with all this, we have a very large spectrum of transducers with different setups to address this. Now, the other thing also that we want to avoid is getting disturbed by noise. So for this purpose, we have coded signals, and when the signal is expected to be received by the opposite transducer, it will open a window at the time expected for the signal to be received. So there's no need for that to get the window wide open during the whole cycle. It only opens when it needs to open, so that it doesn't capture too much noise that is surrounding the environment. So there are also different types of transducers, the shear wave and the lamp wave, which has a wider beam. So in other words, the shear wave is a very focused signal and works in all the possible applications. It can be extremely low pressure gas when it's wetted, and it can work in very high pressure liquid or gas in either way. On the lamp wave, you use the wall, the pipe wall, as a waveguide, so it kind of resonates in the pipe wall and it spreads a very large beam. So it's sometimes used in gas clamp-on when the pressure is not too big, but if the pressure comes too big and the pipe wall comes too large or too thick, then it needs to go back to the shear wave again. So you need to be very careful when selecting lamp wave. You need to know perfectly what the wall thickness is, as well as the pipe material of construction, to make sure that you get everything optimized. So this is also a possibility there, but you need also to be very selective on the lamp wave technology. Okay. So as I said, we have coded signals. So what you see on the left is a coded signal from what is a kind of sinusoidal shape originally sent. And once the signal is received, it's kind of superimposed to what has been coded, and it's checked to verify that the shape that has been sent does correspond to the coded one. So on the third row, you can see that the correlation is quite good because it matches the code, while the one underneath on the final row is not correlating very nicely. So there are probably other issues that have occurred there, and we cannot get something very good. And it can be driven by a lot of noise surrounding the application. All the ultrasonic meters, again, whether you use that or not, have extensive diagnostics available. So those diagnostics will help to put an assessment on the health of the instruments and the quality of the readings, right? So the first one that you need to look at will be the velocity of sound, because if this one matches the theoretical one that is available from different literature and as well as in our documents, then you get this correct and you can start looking at the other ones. If the velocity of sound that you get is not within 1 or 2% at max from the theoretical value, then you need to understand why, because it's probably not wise to look at the other diagnostics once this one is not properly addressed. Okay. Our transducers, when we are using them in the field, whether it's general purpose or hazardous areas, we can send very high voltage on the crystal piezo, which means that even on hazardous areas, we are not intrinsically safe but explosion proof, which allows a high voltage to be sent to the crystal piezo that will provide a larger peak-to-peak signal that will help to address difficult applications. We have also for special applications the buffer guides that are using a patented system. It's kind of a sort of big acoustic guide. If think about fiber optics, but that will be magnified 1,000 times. So it helps to have a very sharp and nice signal. So the signal to noise ratio is getting improved when we have such a setup. And when we put the transducers at the outside so that it can be easily replaced without interrupting the flow, it also gets a proper signal propagating into the fluid. So these are the few things that we have developed through the years at Panametrics. And as a summary, we have different sets of liquid meters. So clamp-on, worded systems with flow cells or insertion types, as well as very high-end meters for extremely high accuracy requirements. We have also a large portfolio of gas meters, again, clamp-on, the worded systems, steam and flare. So flare being probably one of the most difficult one because of the difficult conditions and varying conditions we typically see on those applications. So for liquid, we start at 1/2 inch and we can go on very large sizes. So 300 inches is a possibility. It typically happens on the very large cooling water lines, or you can also see that on the power gen on the penstock. Penstock, to my viewpoint, to my experience, is where you have the largest diameters just downstream the dam. From a temperature standpoint, we can handle cryogenics. So we have a lot of applications on LNG, for instance, which is the transition gas or the transition fuel that the world is using for the next probably 2 to 3 decades before we move to full sustainable energy. And the meters can use from 1 path up to 8 paths to increase the accuracy, performance, and repeatability. On the high temperature side, we can go also extremely high. Probably the highest temperature I've ever seen is coming from steam applications, where superheated steam can be beyond the 1000 Fahrenheit. And this is where we play. When it comes to liquid, it's a bit lower than that, but it can be up to 850. We have for gas, the biggest lines are typically on flares. It doesn't go as large as we have on liquids. The biggest I've ever seen is in the Middle East for more than 100 inches, but it's common to be up to the 70s. It's pretty commonly, while most of the other applications, inclusive of steam, will be within, let's say, 1 to 2 inches and up to 40 inches. Okay. And pressure-wise, depending on the mechanical construction of the meters, whether it's a wetted system or clamp-on, it can go pretty high, but we need to verify the mechanical integrity of the overall system. So why do we have such good adoption of the technology? So I'm not going to go on all those bullet points there, but we discussed that a little bit on one of the first slides. So I guess you get a point. And one that we did not cover is the low cost of ownership. So as users, you are obviously interested in how much it costs to get a meter on your plant, but you are also highly interested how much you're going to pay to get it running. So it tends to be slightly on the higher sides when it comes to investment, but it's on the very low side when it comes to operations. So if you consider the life cycle of a measurement, let's say 15 to 20 years, it's a good calculation to make, because you will see that the return on investment is extremely quick. So it's not a matter of years, sometimes it's a matter of months. So it depends on the applications, obviously, but it tends to be very effective from an operational expenditure point of view. Right, so now I get into the some of our details that we need to consider when installing a meter. So you have a lot of different scenarios there where you need to prepare for having straight runs before and after the measurement point. Why? Remember, we said that what we measure is velocity. So the velocity that we measure needs to be representative of the mean velocity that we have on the pipe. If we have a single path and if we measure at the center of the pipe, it obviously tends to overestimate the velocity there. So we have correction factors that are kind of automatically running into the electronics to kind of put a 0 point something depending on the flow profile that is expected from a Reynolds number point of view. But we need this flow profile to be developed. So in other words, if you put that just right after a bend as an example, the outside of the pipe, I mean, you will have an acceleration compared to the inside of the bend, sorry, the outside of the bend compared to the inside of the bend. So the snapshot you're going to take in terms of velocity will not be representative enough of what is the mean velocity. So while the repeatability is not much impacted, the accuracy will be impacted. So it is recommended as a general practice to get 10 diameters before the measurement point and 5 after. For gas, it's more 20 before and 5 to 10 after. Having said that, by increasing the number of paths, you can potentially decrease those needed straight runs, but there's a cost associated to it, so you need to balance things out to see what is really requested. Okay, so there you can see that obviously if I have a control valve and if I flow from left to right there, right, then it's not that of an issue of putting a control valve downstream of the flow meter. But if I look just the one underneath, I have a control valve that is before the flow meter, then I need a much longer set of straight runs because the flow profile will be hugely impacted by the control valve restriction to the pipe. It will create a lot of distortion to the flow profile, and we cannot really cope with that nicely. So if you have to have a control valve, put a flow meter before and not after, right? I don't want to go on all of those because there's a number, but sometimes when there's no other options than installing with limited strain runs, and depending what is the expected performance accuracy wise, we can run some computational fluid dynamics and kind of mimic from the isometric drawings that we are provided. We mimic what is the flow profile looking like at a given measurement point, and from there we put recommendations. So you have an example on the bottom right where you have two bends 90 degree, you have one T90 degree, and then you have another bend. It's a 24-inch diameter, and then you have the metal leg with 15D in total, and then another bend. So we should have 25, we have 15. Okay, so what we do, we kind of simulate this piping, we simulate the flows, and we take in these specific examples what is the impact on, depending on where I am in the number of diameters after the last bend, which is the bend right here. So thereafter, you can see that there are different kind of variations here it's a bit. So if I position my meter at 15D there, then I minimize the scatter there. So regardless of velocity, I don't have a lot of scatter there. And I will put some correction factors based on different velocities that you have here. So 1, 3, 10, and 30 in this case, it can be even up to 6. And it will compensate for the offset that we have compared to the baseline that is expected to be 1. Okay. So are there limitations using ultrasonics? Yes. So you might have limited straight runs that will trigger an additional uncertainty of the measurement. You have limitations if you have mixed phases. So if you have liquid in gas or gas in liquid, it needs to be minimized and kept below 5% in volume, not in mass, by the way. If you have a very small line size at a very low velocity, because we measure time, the time will be the difference of time will be very small if you compare to the electronics resolution, and it's probably not the best technology to use. Custody transfer applications, you will have the difficulty when it comes to compact provers. We will need a master meter or a pipe prover to be compared against. And it doesn't work on non-Newtonian fluids. So we see those especially in the food and beverage industry. Milk works, but yogurt does not. Only ketchup, those kind of fluids are non-Newtonians. Okay, but that's about it. Now, if I run into applications, if I look at steam, so we have more and more demand on steam measurement using ultrasonics because of the absence of pressure drop. The rangeability is quite wide, especially if you're on the utilities and you have steam demand varying largely between winter times and summer times, for instance. So this is something that has triggered the move from traditional technologies to ultrasonics. And as I said, from a maintenance standpoint, it doesn't need to be kind of maintained as long as the diagnostic stay within the permissible limits. So there's something though that you need to consider is when we are on a saturated steam application, which means that you might have a little bit of condensate presence. So we talk about steam quality. The steam quality is a mass ratio between the steam as a gas and the steam as a liquid or the condensate. So it needs to be at 92% or more. If it gets below, then there's a high risk of the second phase being too big and we will have signal losses. So if you have the steam quality that is below 0.92, I would not recommend to use ultrasonics, but I would say that the vast majority of the steam applications are within the 0.92 and above in terms of steam quality. So if you have also some risk, it's also wise to make sure that you position the transducer and the nozzles on the horizontal axis if you have a horizontal line, so that it kind of self drains. While if you are with a certain angle and you have one of the transducers and its nozzle that is getting downward, pointing downward, then it will kind of grab all the condensate. You might end up with an acoustic short circuit that we don't want. Okay, so you have some photos there. So the first one on the bottom left is the saturated one. You can see the line is insulated. So in steam lines are typically insulated because you don't want to reduce the temperature to increase the condensate content. And the two other pictures are from the same line. This one is just above the saturation points, and this is a billing system from one plant producing steam for feeding the plant that is next to it. Okay. Because if you have the saturated steam, you need temperature or pressure because it's saturated. If you are superheated, you need temperature and pressure so that the system will return the mass flow that you have in your steam line. Okay, so very important, the steam tables are embedded into our electronics so that you can output the mass flow, which is typically what is used for steam usage. The gas applications that can be utility gas, air, nitrogen, oxygen, etc., any kind of natural gas or other feed gas, biogas, acid gas, etc. So again, the reasons for moving into this direction will be the turn-down ratio, the absence of pressure drop, there's no low flow cutoff, although the error will increase slightly at the very low end, it doesn't cut, okay? And we can have online retraction, which means that there's no downtime if accidentally something goes wrong and you need to replace the transducers, for instance, there's no need to shut down the line. The first photo there is on the gas line. It's relatively high pressure, and you can see there are isolation valves and systems for installing and retracting under operations without the need for shutting down the line. This small guy here is on a 2-inch line on a biogas application. This one is on a fuel gas line of 8-inch. This one is on a coke oven gas on a steel plant. So coke oven gas is typically handled at very low pressure. It can be much larger sizes than the one you have there, but I had another picture. It was not very nice, so I preferred to show this one. So it's a dirty gas, and the calorific value of the gas is not very high. There's a lot of CO2 as well there, and the ultrasonic has proven to be a reliable one. So in the steel industry, we have a lot of those in the coke oven gas, the blast furnace gas, and they can be also online retractable because depending on the trending of the diagnostics, you may need to retrieve the probes, clean them up, get a coke out, and put them back into service. Okay. So when it comes to clamp on, it works both on liquids and gases. While I would say that for liquids, you are 99.9% sure that it does work. For gases, you need to look at a few other things. But the reasons for adoption of the clamp-on is kind of the same, but also because there's no need to tap on the line or to cut anything, there's no HEC risks, there's no contamination risks that are associated to it compared to the other advantages that we covered earlier. So it's particularly relevant when it comes to the very hygienic industries like pharma, like food and beverage, like semiconductor, where you all work in clean rooms. So contamination is a very big deal there. So it helps a lot. So the first photo there is on an offshore platform. It's a gas lift. So very high pressure gas injection. It's clamped on the line. The reason it is clamped, it's because it's an existing line that they couldn't cut because they are producing 24/7. The small one underneath is in an hospital. It's an oxygen line. So it's a very, as far as I remember, it's 2-inch line or 1.5-inch line. The other one that's showing up now is on a huge 142 inches line, which is a cooling water line on a power gen plant. And the pipe is made of GRP, so glass reinforced plastic. So there are lots of these being used these days because it's a light and cheap kind of material. But as you can see on the pit doesn't go to the bottom, so you couldn't strap on the transducer holders. So the transducers have been glued with its holder onto the line. The one that you see there is, I cannot say the brand, but it's an electronic producer. So all the lines are stainless steel because they are kind of clean room, and you can see on one of the lines is CIP, so clean in place, which means that even if in normal operations the temperature at the transducers there are not very high during the cleaning in place, it goes up, but the transducer can withstand those high temperatures without the need of being removed. So it's also an advantage. If you have SIP, so sterilization in place, and you have steam, while this is water being flown there, which means that when the steam will be used, you will lose the measurement because the transducer are set to work for liquids, not for gas. But the temperature will also be a no-brainer. You can keep the transducers online, although they will not read during the SIP. Okay.
Gerard, this is Jim. A question's come across the screen here.
Yeah.
Now might be a good time to ask it. Customer is asking, if I have a gas stream where the gas temperature varies by some 40 degrees Fahrenheit, do I need to recalibrate the meter based upon those temperature changes?
That's actually a very good question. So what will change with the temperature is the velocity of sound. So you remember on one of the slides, we had those kind of window there. So we will need to understand, because 40 Fahrenheit is not very large as a spread in terms of temperature, but it will impact the velocity of sound, and we will need to ensure that the window, once open, is covering the range of the velocity of sound that will be impacted by the temperature change. So that will need to be set during the programming of the meter for installation. So if it goes, let's take another example, it goes well beyond this 40 Fahrenheit, let's say 100 plus Fahrenheit, then you will need to get a function that is called a tracking window, and you put it on because it can be off, which means that when the signal is no more captured, the window will start to move left and right to recapture the signal. But in case of a 40 degree Fahrenheit shift, it will stay within the window. Okay.
Thank you.
Thank you. So on this line that you can see it's a colleague of mine, but he's not super tall, but he's a kind of a normal size. But the pipe you have there is on a dam, so it's just before the penstock. And the diameter, I don't have it from the top of my head, but it's huge. Okay, and you can see that they have kind of used a magnet clamping feature there on the line to get a measurement. I can tell you that 8 companies were there to try to get a measurement, and we managed to get a measurement. So that's a difficult one, okay? But we can measure on very difficult conditions. So this one is probably one of the biggest lines that we ever covered. This one is a mag meter, a broken mag meter. So they actually cut the shroud. You can see the coils up and down, and they clamped the meter to get a measurement, because it was a water supply, and the option was for them to cut the water supply for more than 24 hours, or to get something installed in the meanwhile and get a measurement. Okay, so clamp-on has had a lot of benefits there. This photo also is on a ductile iron. It's not an easy one, but you can see there's another flow meter here installed that is faulty, and we have clamped an ultrasonics to get a measurement, because this water is actually billed to another plant. So that's a water facility that is billing the water they send to another plant. This one is also a ductile iron installation. So it has been clamped there using a dual traverse setup. So
Gerard, questions come in regarding that last slide you've shown, which is the clamp on. Is that just downstream of that mag meter, or is that upstream of the mag meter? And are you not concerned about any additional velocities being created as that water goes through the mag meter?
All right. So if I look at this photo and this one, so the last two, right? The mag meter is a full bore meter, right? So there's no obstruction to the flow per se, right? So in that case, it doesn't matter. You still have the straight runs. If it would have been a turbine meter, for instance, that would have been a very different story, though. Okay. So if it would have been an orifice plate, a very different story as well. But in this case, you are kept as a full bore system using a mag, so that's not a big deal. Okay.
Thank you. I have a couple other questions that have come up. You referred to the large diameter pipe where 8 other companies tried and failed. What was unique, or what is unique about your product that allowed for success?
Okay, so on that one, in fact, you have a very large path length, very long path length. So you will have a lot of attenuation there, because what I forgot to mention there, the reason for the others to struggle a bit is that you are very close to a gate valve, very, very close. And even if the valve is fully open, there's a bit of disturbances there. And our guess, because we could see that there was a bit of noise for the signal. But remember what I explained earlier, we can send 150 volts if we want to the crystal piezo, right? Typically, the way the transducers are designed by others, they have limited voltage being supported at a crystal piezo. So that limits a little bit the capability there. Secondly, remember the coded signals. So if you do not code, you get a lot of noise that it's very difficult to filter. If it's coded, then you kind of filter the noise that is present there. So I can say that it was not the easiest one. I don't have the photo here. I didn't put that one, but we also did a test in France with EDF, which is a national energy supplier, on a dam, and they were changing the switches, the flow switches. They were mechanical flow switches, and because they were breaking them once every few months, they wanted to get ultrasonics, and what they were not sure is that what is the maximum capability velocity-wise. Our system is normally designed to handle in feet per second is about 36, close to 40 feet per second. In this specific test, we were up to 75 feet per second on a 5 diameter pipe, 5 meter diameter pipe. How much is it in foot? Yeah, so let's say 16 feet, right? So huge. So it was unexpected, if I'm honest. So it was a bit noisy as a signal, but the measurement was there. So that's basically our expert. Sorry.
Thanks, Gerard. And we had one last question, or at least at this point. Can you use clamp-on on lined pipe?
Yes, so that's another good one. You have very good questions. So if you look at the mag meter there, where it is clamped on the mag, that's actually a lined pipe, because you have, it is typically stainless steel there, and you have a PFA or PTFE liner there. So what you need to have when you have a lined pipe is you have an understanding of what the thickness is of the two materials. Because what you do when during the programming, you will enter the material of construction in on both and their respective thickness. Because there are tables in the electronics that says that if I have stainless steel 316 and I have this thickness, I know that the sound will travel at this velocity, so it will take few milliseconds to travel the wall. And when I get into the PFA, because it's less dense, I will also have a kind of diminution of the velocity at which it travels, but I still need to know this one because it's kind of a dead time. So I don't want to be influenced by the time it takes for the sound to travel those thicknesses. So I need to enter the proper respective thicknesses of the two materials, and so that I only focus on the time of the signal in the fluid I want to measure. So we can do line pipe, but we cannot do 3 liners. We are limited to 2. Okay. You've seen also that we have, I just want to show some pictures. So we have this kind of portable. This portable is very handy if you have to assess a pump. For instance, on your plant, you have many pumps, and you know that the pump is expected to deliver a certain height at a given flow rate, but are you sure it's still delivering of what is designed for? So if you know the pressure and you need to know the flow to ensure that the pump is delivering as per its original specs. So we did that. This is also, this photo is from California, by the way. So this is also an irrigation line that feeds many different plants downstream of the dam. And they have an inline meter. It's not shown in this picture, but they were willing to cross-check. It's not for a pump, but it's also for cross-checking an existing meter that they have installed that. And you can see also it's a magnetic clamping fixture there. And on that one
Gerard,
is a...
Gerard,
yeah.
Gerard, I have yet another question. Sorry to interrupt you.
No worries.
The question is, so on dirty pipe, should we guess the thickness debris on the walls?
Oh, that's a difficult one there. In fact, we would recommend there's a thickness gauge that comes with a portable as an optional item. So we would recommend to take the thickness not only in one point of the pipe, but different points. So you take 4 points, you know, evenly distributed, so that you have the thickness measured on those 4 points and you get an average. If you have debris, they will unlikely be evenly distributed in the inside diameter, so that may slightly impact your calculation. Remember what I was just talking about? We enter that this is, for instance, a carbon steel or ductile iron, whatever it is, at a given thickness. If you have a bit of debris or buildup inside of the pipe, it will certainly create a slight error on your volumetric flow rates, not really on the velocity per se, but on the volumetric flow rate, because remember, you multiply the velocity times the cross section of the pipe. So if the cross section is not what is kind of reflected, it will be difficult. And when you have your thickness gauge and you measure the thickness at different points, because you have entered the thickness gauge, what is the material? If you have a coating on the pipe, it will have a different density, so it will not really be accounted for. So you may trigger a little bit of additional error, but our experience says that this error will be maintained typically in a couple of %. So this picture also shows on a fire water pump. You can see the line is clamped, so it's not very common to have permanent flow meters on the fire water pumps. But when you do the dry runs, you need to ensure that also the pump delivers, as we discussed previously on the curve, for the flow rate and the height it is supposed to deliver, and you can easily cross-check this with a clamp on. So this one is a sewage water, so a lot of solid content there. You can see there's a mag. Upstream of the mag, in this instance, we have our clamp on, and there's another clamp on that is upstream our clamp on. So there's no measurement here because this one was faulty. This one couldn't get a proper measurement because they had no signal, and we got very good signals. Again, think about the coded signals, think about the powerful transducers that we have used. This is a dual traverse setup, which means the signal goes and bounces back the opposite side. And even on this sewage water line, we got the measurements matching the customer's expectations within 3%. All right. I don't know if we have a lot of people in line that are using flare meters, but flare is probably the most difficult measurement to make, essentially driven by this 4,000 to 1 turn-on ratio from extremely low flow down to 0.1 foot per second up to 400 feet. That makes the measurement super difficult. Accuracy-wise there, the typical kind of standard is calling for 5% of reading. And we have also a large variations of hydrocarbon mixtures. So if I remember the previous question about, I have my gas, temperature of the gas varies of 40 Fahrenheit. In this case, it varies about 200 Fahrenheit, and the gas composition varies from hydrogen with a very low molar weight up to ethylene, for instance, with a very high molar weight. So that makes the measurement very difficult. So the window in this case is way larger, but that's at the expense of the accuracy. What you need there is to measure regardless of the flowing conditions. So again, this is not probably as tight in terms of performance accuracy wise, but it does work. And Panametrics was the pioneer there because we patented together with Exxon back then in 1984 the first flare meter. And these days we have thousands of those installed throughout the world. I don't want to repeat all the kind of stuff that I explained. So you get most of the common themes. So turn-on ratio, independent of composition, although you will kind of have the tracking window that will move a lot when you have changing conditions. We have different set of transducers to cope with the fairly large temperature span that we can accommodate. So that's really what drives the unique capabilities we have in our product range in general, is the experience we have gained in these very difficult applications. We have also LNG, as I said. So the picture on the bottom left, we have redundant meters on the heater passes, very high temperature there. You can see the sketch just above it, where you have one measurement that goes into the control system and 3 measurements that are going to the emergency shutdown system. And unlike other technologies, it's an actual redundant setup because you have 4 different electronics, but each electronics is attached to a set of transducers. So it's an actual redundancy. It's not like if you have an orifice plate with a quadruple redundant DP cell, diffusion pressure system, because if you have an issue with the primary element, which is the orifice, then you treat all 4 at once. While here, if you have an issue with one set of transducers, you have 3 others that are still running. Okay. So yeah, this is also the last photo is on the very high pressure injection line in oil production. So we have a wide experience in there, and there's something I would like to mention as well. We talked a little bit on the power gen. So the boiler feed water lines as well is a very critical measurement because it's what is delivering the power basically. So the flow meters installed on the boiler feed lines, they need to be typically redundant. It's sometimes a seal rated measurement, and they want to be trouble free there. So we started to see some requests on those applications about a couple of years ago. We were not really in this segment, but we start seeing quite a bit of requests using ultrasonic technology there. And I will end up with the high accuracy stuff where those meters are used in North America for leak detection applications. So they are using these to track the line balance on the pipelines. They are height path meters, so they are very accurate, and they are calibrated so that they are viscosity independent. I don't have time to go into the details there, but it's very, very interesting as how we do it. And the photo on the left is a metering station for oil, and we replaced turbine meters there, not because they were not accurate. It's simply because they were having a lot of operational expenditure costs with them because of the drift over time, because of the let's say lifetime on the bearings, on the blades, etc. So that's about it. I've taken a bit more time than I was thinking, but it's very good that I had questions. But we have the deck still open for questions. Jim, did you get other questions? Okay, so there's one question about calibration. So do we need to calibrate those meters? Because we're on the slide of high accuracy, and if you are on a physical measurement, the answer is yes, you do. If you're on a flare line, and because you need to comply with some of the regulations, especially in the United States, it's not a calibration per se, it's what we call a verification, because calibration means that you compare versus a traceable reference that is certified. It's more a verification because it's not practical to calibrate a flare meter. So in this case, I would say yes again. If you have a process meter, and if you have the diagnostics that are staying within the permissible limits, when there are thresholds, there's a high threshold and a low threshold. So if they stay within these permissible limits, it is not required to do anything around calibration. If you have the velocity of sound that stays within the expected range of what the theoretical value of the speed of sound is, there's no need. So in other words, unless you have a regulatory requirement, there is no need for recalibration because the technology by itself is not prone to drift, right? But I would recommend that once in a while you look at the diagnostic parameters to ensure that there's none of them that is outside the boundaries. Okay, so time is up. So I want to thank all the participants. for your time. It's very much appreciated. And Lesman and ourselves will keep close to you, whatever new questions may arise, and we'll be available for any demonstration if need be. Thanks very much for your time.